All right, hello AP Statistics. This is section 8.3, estimating a population mean. You're going to need your T distribution table. You will need a graphing calculator, paper, pencil, your note sheets, and let's get going. All right, so let's reflect back just for a second before I get going. This says estimating a population mean. That's my title. Okay, that is true. That doesn't change. But I want to talk about 8.2 just for a second. Okay, 8.2. Running on the top, dealt with population proportions. Okay, and we identified those with a P. And we said, you know what? Population proportions are too difficult to find. Okay, populations are just too big. So what do? We use sample proportions to help estimate, okay, what our population proportion may be. Okay. All right. And so now we have 8.3, okay, which is similar to this, but instead of dealing with proportions, we deal with averages. Okay. And again, this is a population average for mu. And again, we accept the fact that sometimes populations are too big. So what do? We use a sample average to help estimate what we believe the true population to be. Not the true population to be, true population average to be. Okay. Now, one of the unique differences between 8.2 and 8.3, okay, dealing with proportions and averages, deals with critical values, all right? And so here we use Z's, okay? Z's in 8.2 were used for critical values. Here for 8.3, we're going to deal with something called T's, okay? And this is under the assumption that our population distribution may not be exactly normal, okay? And what that means is our sampling distribution may have different representations for their curves, though they will look somewhat similar in some ways, okay? And so let me explain for a second. We're dealing now with T's, and you'll notice the set of directions that says use table B, okay, to find the critical value T, not Z, that was 8.2, okay, for a 90% confidence interval for a sample of 10 people. Okay, now here's the deal. I'm going to have you use a little formula. It's really easy. It's called degrees of freedom. And I don't really want to write out the word degrees of freedom every time, so I'm just going to call that DF. Okay, is equal to this formula, very small, n minus 1. Okay, and so in this case, my n is 10. 10 minus 1 is 9. Okay, now what this says is this, and I'm going to draw this in a different color just to start. If my normal curve looks something like that, and that's probably the best I can do with a little sketch. Okay, I'll put a big N here with a normal. Okay, what it means is that my sampling distributions for samples of size 10, which gives me a degrees of freedom of 9, is not going to look exactly like this. Okay, especially if our sample or our population distribution of items is not exactly normal. Okay, and so what this means is I'm going to have a little bit more unique looking curve. I can share that the peak will be centered around the same spot. Okay, we're still going to have an average of 0. Okay, however, the tails will be a little bit higher, and the peak will actually be a little bit lower. Okay, so you'll end up having something that kind of looks like this. I can draw this well. Okay, so you still got a curve just like before, but again, it doesn't go as high. Okay, when it's in the center where the peak is. And again, the tails, okay, the tails are going to be a little bit higher as well. Okay, and I exaggerated this a little bit just so you can see the difference between the two. They line up a little bit closer than what I showed you here, but it gives you some representation of what's going on. Okay, so this would be a degrees of freedom of maybe 9. Okay, had you dropped your degrees of freedom even more, and I'll just make up something else here in green, if I say my degrees of freedom is say 3, okay, then again, it's not going to be as high. Okay, and it won't be as high in the center where it's supposed to peak. However, okay, the tails will be a little bit higher than what the other representations had. Okay, so the tails will grow. Okay, and you get something that looks like that. Okay, degrees of freedom of 3. That's just an exaggerated rough representation. And the idea again is that for every sample size of n for sampling distributions, okay, for means, we come up with this idea that each sampling distribution of a certain size n will give you a slightly different shape, okay? And if they give you a slightly different shape, okay, then that means we have different values for critical values for different percentages, whether they're 90% confidence level, 98, 99, 95, etc. Okay, so how do we find our critical value t's if they're not going to be the standard z ones that dealt with 90% being 1.645 and 95% being 1.96, etc. We're going to use this new table. Okay, this is called the T distribution table. There's a website above. I'm going to identify it right here. Okay, it's free to copy it from there, and they invite you to do so. So keep that in mind. Okay. All right. So here's what I'm going to do. I'm going to find my critical value for 10 people for 90%, and I'm going to identify that with a T. Okay. Take a look at the kind of like the titles or the labels on the bottom here. Then you got 0, 50, 60, 70. Bottom row, okay, that's your confidence level. And you'll notice, for example, there's ones that we've had in the past. We have a 90, we have a 95, there's a 99 in there. And notice the number directly above it. So for example, if I'm looking at 90 down here, the number above it is 1.645. I'm circling it. And that's familiar to us. We did that last section. That's 1.82. That is the respective z-score. And you look off to the left here. Yeah, that's the value z. Okay, that's the assigned symbol for it. So if you look next to it, 95% is 1.960. Yep, that's the one we used before. 99% is 2.576. Yeah, so these are all items that we worked with yesterday. However, okay, if I have smaller sample sizes with these respective averages, okay, then I'm going to use the items within this table to help answer this question about critical values. Okay, so I know that my degrees of freedom is 9. Notice this left-hand column has a DF at the very top. Okay, and I'm going to go down to 9 and write this arrow here where the 9 is. Okay, and I'm going to scroll across until I match it up with a confidence level that matches question number 1. In this case, the first part of question number 1 says 90%, so that is right here. I'm going to go up until I get to that 9, and I wouldn't circle it on my chart like the hand, like the one that's printed in front of me, but I can on this computer screen because I know it'll erase. That'll give me 1.833. Okay, and so that is my critical value. It's kind of like a game of Battleship, just kind of go over and across based off your degrees of freedom and your respective confidence level. Okay. If I do another one, it says table B. I'll do this in a different color. I'll do it in purple. Again, my degrees of freedom is n minus 1. So 27 minus 1 is 26. All right, and 26 is down here for my degrees of freedom. I'm pointing it out with my far left-hand column. And 98% is to the right on the bottom. And if I scroll up, I think I have, looks like 2.479. 2.479. Looks good. Okay. And then finally, for table B, you have a 99% confidence interval. So here's 99 on the far, almost far right. Okay. And I'll do this different color. Blue. And 43. So let's do degrees of freedom for that. Degrees of freedom is equal to n minus 1. If you plug in 43 minus 1, you get 42. Okay. Now, you have some conflict here because if you look for 42, it's actually between the 42 and the, sorry, between the 40 and the 60. Okay, and like, what am I supposed to do if it doesn't line up exactly on the degrees of freedom I want? And so what you have to do is you have to go with a lower one, always. Okay, always go lower. Okay, so I'm going to go with 40, and I'm going to go over to where the 99 is. So 99 is over here, 40 is there, and I believe it gives me 2.704. All right, so that's how those go. Now, someone asked earlier and it said, hey, what if my degrees of freedom, okay, is for 99%? Say it's say your N was 100, okay, and your degrees of freedom is 99, and you're looking up 99, you're like, well, it's between the 80 and the 100. It's really super close to 100, but can I just pick that over the 80 because it's so close to it? And the answer is no. Okay, you always have to go with the one lower, no matter how close it may be to the one that's slightly above it. Okay. Um, so yeah, you always have to go with the lower one no matter what. Okay. Observe your just your t distribution here, and if you look at, for example, 95%, because that's one that we have used quite a bit. That's right here. That's 1.96. Notice that when your n is super big, that your critical values are almost the same as the z. Okay, they're very very close. Okay, so so there you go. Sometimes I'll tell people that when your n is smaller, sometimes it doesn't feel as trusting. Okay, when you pick smaller samples, and that is why your values here get bigger. Okay, as n gets smaller, your critical values get bigger, and that means your interval is getting bigger. And so there's a little bit less trust, so they have to widen the gap for your confidence interval as you make those estimates for your population parameter mu. So, okay, let's move on, and let me show you how I'm going to use this, okay? All right, so I have this issue. It deals with cell phones, and it deals with the teenagers that I've had in my house, as well as the teenagers that I work with in schools. And it's not a super annoying thing, but it's just a compulsive order that some of them have regarding their cell phone charge. And it doesn't matter how charged their phone currently is, they sometimes always want a bigger charge. And that I see that in my classrooms as they try to sneak their phone charges into the outlets in my room. It's like, get those out of there. Or sometimes I'll see in my own car, it's like we get in the car and there's teenagers in the back, and it's a race to see who can get to the USB ports in the car, or the cigarette lighters in the car to charge their phone with their phone chargers. And it's like, it's ridiculous. Okay. Nevertheless, in my 5th hour today, and we were not in school today. We were in school, but we were virtual learning. So all my students were at their house. I asked them over the internet, said, hey, in my chat, I want you to type in right now, what is your cell phone charge right now? What capacity do you have in terms of energy, in terms of your phone? And I typed mine in first. Mine was 83. And I asked what theirs were. And I said, we're going to use some information to figure out what the true population average would be for all cell phone charges. Okay. Now, is it possible for me to find the true mu? And I'm going to put this on top. Mu is the average cell phone charge. And I know it's a percentage. Can we find that? No, I can't ask every person on the planet what's your cell phone charge. And even if I did, I can't take the time to average all those together. Okay. But maybe I can do a small X bar. Okay. And then use that to help predict the population. Okay. So what do? I asked everybody to do that. And here's the data they gave me. Okay. Of the 18 students who were online and had a cell phone with them, those were the charges they had. Okay. And I was one of them too. I had 83%. I'm right down here. Okay. And what I did is I asked them to put it in their graphing calculator, put it in their L1, and they were to do a 1var stats. Let me write this down. So you are reminded, this is TI-84. I'll put it right above the screen here. 1var stats. Okay, that's the command you'll use to average all of your values in your L1. Okay, and that's what I did. I put these all in L1. And when I did that, it gave me this information. Okay, it gave me the mean, which is my X bar, that's right here. And the standard deviation I'm going to use is S of X. Okay, and what does that mean? It means amongst the students in my class, their charge varied by 31.75 from the class average. Okay. All right, so we're going to keep that handy, and we're going to use that to find a confidence interval for the true population average charge for cell phones. Okay, but first, okay, while I ask this question up here in the left-hand corner for a 95% confidence interval, we have to identify conditions. Okay, now I'm going to lie and cheat a little bit here on this, but I want to explain where they are and explain why I have to lie and cheat on this, just because in the end, if I looked at this, it says random. I know you're not random students, okay? You're not random people with a phone, actually. It's not possible for me to take every single person on the planet, put all their names in a hat, and pick 18 without replacement. Okay, you just can't do it. And I just wanted to use data, practical data that we had. And so I just use fifth hour data. And so typically we need this. We need random, and we need to look for it. Okay, when they provide us with a new problem. Okay, so I am going to I'm going to say this is we had a random drawing of people, even though it really wasn't. Okay, you knew that you're a fifth hour and you're special, and I love you to death, but it really wasn't random, and I think you understand that. But how else are we going to collect data? Okay, the second one is large samples. Okay, large counts for normality, and what we want to know is our sampling distribution going to be approximately normal. Okay. Now we did this back in chapter 7. Okay, and I'm going to write some information just above this number 2 here. Remember that if n was greater than or equal to 30, we were like, yes, by essential limit theorem, yeah, our sampling distribution is approximately normal. Okay, and you're like, cool, we hope that our n is at least 30. Was it in this case? No, it was 18. Okay, and you're like, that stinks. Yeah, it was 18. Okay, what does that mean? Well, that means is what we have to do is look at our data and provide some type of graph to make sure that there is no skewedness. Okay, some type of graph to show no skewedness. Skewed. Let me erase that. That's going to bother me. Okay, or outliers. Okay, and how do we show that? We got to make a little graph, and I'm going to do that right now because it's easy. Here's the thing. I got items as low as 0 and as big as 100. So I'm going to actually count by 20s and just see what this kind of looks like. 60, 80, 100. And I'm going to go one more. You're like, why are we going to 120? Because you can only have 100% of charge. I'm going to label this, as you always should. And it's because of this. If I'm making, for example, a histogram, and I'm saying, for example, between 0 and 20, and if I have a value that lands exactly on 20, know that 20 doesn't go in the middle here. You don't put like an X there. And if you have to decide between the left and the right, it always moves to the right. Okay, so when I look at this and I have cell phone charges and I'm only looking at integer numbers, whole numbers, yeah, it's going to be 20 basically to 39. Okay, and then the 40 that you see here will actually be to the right. Okay, could you have a 39 and a half? You may, but it doesn't show it that way on your phone. So, all right, so let me look at my graphing calculator, and I'm just going to put these in, and they're the same ones that were on your chart earlier. And it could be that your class is doing something different, or not doing something different, but have different representations for cell phone charge. So I have 83, 0, 21, 93. That's over here. 60, 45, 83, 60, 45, 83, 77, 3, 39, 9. 41, 14, 57, 63, 100, 82, 39. And that's all. So let me make sure I have 18 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, that looks good to me. Now, here's the thing. I didn't draw these well, so I'm just going to say, hey, my 4 go here. Okay, 3 is a little bit lower. This 3 is the same. Sorry. That 3 goes the same. 4 is a little bit higher. And of course, I've got this one. And does this look skewed? No, I don't think it looks skewed. Okay, it's we got 4 here, 3, 3, 3, 4, and 1. Okay, so I don't think it looks skewed. I don't think there's any outliers here as well. I do have some that are in the 90s here, so I think we're good. Okay, there's no skewedness and no outliers. Okay, so the large samples test for normality because my n was less than 30 is satisfied. Okay, last thing is the 10% rule, and 10% looks like this. It's little n is less than or equal to 1/10 the big N. My little n is 18. We already know that. And what is big N? It's the population of all cell phones. Okay. Okay, so I'll write that kind of small. Get that back. I got the right one. Okay. All cell phones. And what does that mean? Yeah, that's satisfied. In order for this not to work, we'd have to have less than 179 cell phones on this planet. I know we got quite a few of them. Okay, so all of our rules are satisfied with respect to 2 and 3. I'm going to say that 1 is also satisfied, even though you are not random students. The data I got was actually not random. It was from my 5th hour, but that's really the only way I could obtain data of this nature. Okay. Okay, so let's do this. Our conditions, this is always step 1, is we're going to say satisfies. So we're going to put a little asterisk by this 1 here because we know you surely aren't random. Your X bar we shared from the previous slide is 55.9. My S of X is 31.753. And our N is 18. Okay, so what does that mean? Oh, we already had that, sorry. What we need is we need our T in order to submit that into here, and then we can create a interval. Now, in order to do so, we need our degrees of freedom. I'm putting it next to this n here. I'm circling that. Degrees of freedom is n minus 1. And so n is 18 minus 1, which is 17. And so if I look right there, there's 17. 95% is this guy, I believe. Yes. Okay, and if I go all the way up, I got 2.110. Okay, so this will be my critical value for this problem. It's going to replace what our typical z will be with this t. Okay. All right, now for the sake of room, let me move to the next slide and see if I can get this all in. All right, and let me get the formula. And so let me write it to the left here so you can see it. It is, once again, 55.9, okay, plus or minus my t. Now my t we said was 2.110. 2.110 plus or minus the S of x, which is 31.753 divided by the square root of 18. All right, so 2.110, crud, sorry. Let me erase this. Small error. I don't want another plus minus there. Color, purple. Times, okay. And here's what I'm gonna do. I'm actually gonna do that math, okay? I just wanna do this. It'll make sense in a second why I do it. Some people are like, can't we do this all at once, this whole back error piece? And you can, but I'm gonna need this part right here of the formula that I'm circling underneath me in a second by itself. So this gives you 7.484, okay? And if you multiply that by 2.110, you get 15.791. Okay, and of course I'm going to add it and subtract it to this 55.9. Okay, that will leave me with 40.108. Okay, and the upper part of my interval will be 71.692. Okay, and so those are my boundaries for a 95% confidence interval. Okay, and that is the rest of step 2. Okay, and what do I do with that? Well, I go to step 3, and I'll put that underneath this formula. All right, and we're going to write a confidence interval. It says we are 95% confident the interval from 40.106, sorry, 40.108 to 71.692 captures the true population mean cell phone charge. Okay, we are 95% confident the interval from 40.108 to 71.692, you can put percent behind there if you want, captures the true population mean cell phone charge. Okay, and that is it. That is your third step. It has 3 steps just like before, your conditions. Your second step is your kind of like your math, okay, the math part, the calculation part using the formula, finding the interval, and then your third one is to write the sentence, okay? All right, now, some people will ask, is there a calculator to do it? Yes, there is. There's a calculator way to do the replacement for step 2, okay? Not that you don't have to write the answer in the end. However, I want to talk about this ahead of time before that. I want to look at this. It says interpret the standard error of the sample mean standard error of x bar, which is equal to s of x over the square root of n. Okay, basically, what is the standard error of x bar? Here's what it means. Okay, we know what this calculation is, and I made you do it earlier. It's 7.484. I'm just going to write it above here, just lightly, and I'm going to write a sentence. Okay. And it's going to go like this. I'll say for all samples of size 18. Okay. Sorry. Yeah. Each x bar, okay, each sample average, okay, will vary by 7.484 from, I'll say that will vary. Let me put this in, on average. I'm going to bring that in there, by 7.484 from the true population mean cell phone charge. Okay. For all samples of size 18, okay, each X bar will vary on average by 7.484 from the true population mean cell phone charge. Here's the idea. Every group of 18 people who have cell phones, okay, will give you a different X bar. Okay. Everyone. Okay. And so the 18 that we chose from fifth hour, that was one X bar. Someone else, maybe yourself, could go do a random survey and get 18 different people. You're going to get a different X bar. Everybody's going to get their own X bar. And if I compare all the X bars to the population mean, mu, okay, what we can say is that on average, the population mean mu is going to have some distance between the respective X bars, okay? And on average, those X bars will be about 7.484 from the population mean, okay? So that ends what this idea is, okay? We kind of have an understanding for that. But some people say, hey, I can do step one. I know how to do the conditions. I know how to do a sentence. I know step three. And actually, I know how to do step two. I know how to do all the math for that. But is there a shortcut using the TI-84? And the answer is yes. And so I wanted to finish the screen before I moved on because I needed some of this information to help answer this. But here we go. Same question, okay? And I'm not going to do step one. I'm not going to do step three. There's the formula just like before. But here's what I'm going to do. I'm going to look at my L1. I'm going to put all that information in there. In fact, it's already in there. Okay. I'm going to do this. I'm going to go to stat. Let me write this above here. Okay. And then I'm going to go to test. Okay. And instead of going down to the letter A like I did in 8.2, I'm going to 8. Okay. Which is T interval. Okay. When you do so, okay, you're actually going to have two items. You're going to have data and you're going to have statistics. Okay, that's the first thing. If you hit data, okay, and I'm sorry I don't have that slide in here. It's all you're going to do is type that L1 in there and then go through and hit calculate, and you're going to end up with the answer that you see here. Okay, so this is if you have all of your data in L1, which we typically do. Okay, take a look at this answer, 40.099 to 71.679. Okay, if you remember from before, we had 40.108 to 71.692. Are these close to what we found by hand? And the answer is yes. Our calculator version is very, very similar to what we had earlier. Which is the better answer? Of course, your graphing calculator is. Okay, TI-84. Okay. Had you hit in between here, had you hit statistics, okay, then all that means is you have to input your values for your X bar, your S of X, etc., and you know what those all are. Okay. We did those with a 1 bar stats, and sometimes they'll actually include those in there if you've already pre-done that command. Okay. So, so yes, are you allowed to use this for step 2? Yeah, for step 2. Okay, then all you're going to write is TI-84, T interval. All right, and then give the confidence interval like we just did right here, and then move on to step 3, where you would get that answer, the final statement. Okay. All right, so that was the question that dealt with cell phones. I have another item with cell phones, and this is a similar type problem. Okay, so if you feel like you understood part 1 pretty well, then that's fine. You can move on and skip to the last question, question 3. But if you're looking for a little bit more practice, okay, here's the second piece. Okay, and it's pretty much the same type of work. I have some sample scores for this this emoji app that you can get for free. And what it does is if you play it and you get certain scores on it, then it allows you to have Disney emojis on your text messaging features, okay, which is kind of a cool thing for me. And so to find, again, the population average, okay, average score, okay, I'm going to say the population average score for Disney emojis. And again, it's a game. You can check it out. It's fun. It's addicting. Okay. It's unknown. It's like, how do we find that? There's too many people playing every day. There's just too many people who have the app. Okay. But let's pretend if I took all the scores that existed and found 18 different random players' scores. Okay. And they existed right there. Okay. Is it possible to maybe find some type of interval that would contain the maybe true mu? Okay. So first thing I'm going to do, I'm going to test the conditions, okay? And the first one, see if I wrote them in, I don't think I did, is random. And what I want to know are these scores random, okay? I know they're not from my 5th hour, okay? The fact that my 5th hour from the previous problem had 18 and these scores also had an n as 18 is just coincidence, okay? So, but yeah, these are random. It says right here, I'm going to circle this really kind of loudly here. It says they are random, and so this is satisfied. Okay. The next one is we'll just say large counts. For normality. And again, anytime I see this, I lick my chops and say, I hope n is greater than or equal to 30, so I can say central limit theorem, and the sampling distribution is approximately normal, and it's not. Okay, your n is actually less than 30, n is actually 18. Okay, and so I'm going to just count by 10,000s because I want to. Now, the lowest one is in the 30s. Okay, so I don't have to go all the way to 0. Let's zigzag that if you want. So I'm just going to say this is 30 cat thousands. This is 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, 100,000. And again, anything that's 100,000 or more will go to the right. And actually, I have nothing that big. Okay, these are scores. Okay, and again, I'm looking for no large skewedness. Mild skewedness is okay. That happens. You know, nothing's usually perfect. Okay, and no outliers. All right, so this will make this easy. That's in the 30s. I'm just going to go down. Okay, 54 is the second one. 80, 78, 72, 57, 66, 73, 43, 90, 65,000, 48,000, 61,000, 69. This was looking good, actually. There's 93, 83, 81, and 74. Okay, and if you were to ask me, does this look skewed? No, it looks pretty good. Okay, are there any outliers? None. So again, I'll put a check mark saying that I think we're pretty good. Okay, I think that was satisfied. Last thing is 10% rule for standard deviation. Okay, so what is that? That's little n is less than or equal to 1/10 the big N. So my little n is 18. Do I believe that there are more than 180 scores for this particular game? Yes. In fact, I've had some of those 180 in a week. Okay, so I know that that's certainly true. That's all satisfied. So step 1 is done. Okay, so this is step 1. We are good. Okay. Step 2, I want to use the graphing calculator. Okay. Make this easy for myself. That way I don't have to use the chart to look at my T, okay? And as long as I put all those in my L1, okay, I can just go through and work it out and finish it. So in this case, they ask for a 99% confidence interval. I'm going to look at that right here. Again, for the true population average for the Disney emojis game. Okay, so here's the top TID4 representation. Okay, I'm going to go to edit. I'm going to put everything, in this case, into my L2. Okay, and I'm going to go to stats. Just to remind ourselves, stats, tests. Okay, and again, everything in this 8.3 will go to 8. Okay, and so we'll go to interval. And here's the slide I forgot before. But this is data. Okay, all your data is actually an L2. So let me change that and I'll highlight it. It looks like an L2 right there. I'm going to put in 99% right here. Okay, but again, don't forget to put L2 there. Go down to calculate, and you end up with this. Okay, so if I'm showing information for step 2, okay, I'm just going to say TI84, T interval, and I'll write the interval, 56,923 to 79,432. Okay, and what does that mean? Well, off to step 3. Means I don't really know what the true mu average score is, but I am 99% confident. We are 99% confident. The interval from 56,923 to 79,432 captures the true mean Disney emoji score. Done. Okay, so again, step 1 are the conditions. We did them on the previous page. My hope is that your n is bigger than 30, because if it is, makes things kind of sweet. Okay, because all you have to use is the central limit theorem for the large counts. But again, do the other 2, random and 10% rule for standard deviation. Again, this is step 2 right here. If you have the opportunity, okay, then use your TI-84. It's much easier to do it this way. It's also a little bit more exact. And I think, in my opinion, you have a little bit less chance for error. Sometimes people will say, hey, you know what? Sometimes they'll give you a list of data. Okay, they actually tell you what the X bar is, or they'll tell you what the S of X is. And again, if you're using your graphing calculator, if you look at this slide, it's like the 4th one in. Then what you'll do is you'll click stats. Okay, and if you click stat, it'll tell you some input values for your X bar and your S of X, etc. Okay, and you just finish it the same way. All righty, we are done with this one. It wasn't much different from the other, but you can see how, as we transition, a little bit more smooth it goes when you use your graphing calculator. All right, here's the last one. It says the average amount of ice cream eaten per year in cups is defined by the normal distribution with a population standard deviation of 21.3. If we want to calculate a 90% confidence interval with an error no larger than 2, how large of a sample is needed? Okay, so remember that error is this back piece. Okay, and we did this in 8.2. Okay, we took this item, I'll put it up here, T times S of X all over the square root of n. We said, hey, this has to be less than or equal to what they share, 2. Okay, so 2 is highlighted. I'll put that there. And some of you look at this and say, you know what? I know that I need to solve for n because it says how large of a sample is needed. Okay, so this is what I'm looking for. The S of X isn't really given here. Okay, it gives you a population standard deviation, but not a sample standard deviation. Further, you're saying to yourself, you know what? I know how to find T's. I'm going to use my chart. Okay, it tells me the confidence level is 90%. And so all I have to do is look at my chart. I'm giving you this little chart down here. Look at 90% and go up until I find my degrees of freedom that match. Okay. Now degrees of freedom is n minus 1. Okay. However, we have an issue. Okay, because if I ask you to find the degrees of freedom, you're kind of sitting there and saying, I need an n, and I don't have an n. In fact, that's the problem. You're trying to find out what n is. Okay, and so because of that, we have to adjust. Okay, and what that means is that we're going to use a z as opposed to a t only in this one case. Okay, so I'm going to put this in big bold letters. For this section, if we are solving for n, okay, for problems dealing with error, okay, for problems relating to error, we have to use a z as opposed to a t. Okay, and because we can't find the degrees of freedom, okay, degrees of freedom are unknown. Okay, further, we're also going to use a population standard deviation over the square root of n to help guide us. Okay, and so what is z then for a 90% confidence interval? You know that is 1.645. Okay. What is your standard deviation? Well, you learned that earlier, 21.3. There is your square root of n. Okay. Now, what do I like to do? I like to multiply those together. I just do. That will give you 30. There's a lot of ways you can solve it. So my way may not be your preferred method, and that's okay. You can do it your way if you want. 35.0385 over the square root of n is less than or equal to 2. All right, and so you have to multiply both sides by the square root of n. And that makes these go away. Oh, nice. And 35.0385 is less than or equal to 2 square root of n. Let us divide both sides by 2. And if you do that, you get 17.51925. Now, most common mistake, people are like, okay, I've got one more step, okay? And what they'll do is they will square root this answer, okay? And you don't do that. You have to do the reverse operation, okay? You have to ask yourself, how do you get rid of the square root? And you do that by squaring this side and squaring that side, okay? When you do so, you get 306.92. And keep in mind that you always round up. So in this case, your n will be 307. Okay, even if like, for example, the 2 and the 9 were reversed. Okay, say you had this. This is just okay. You would still round up to 307. Okay, so why do you do that? Well, here's the idea. When you look at your inequality here, all right, as n gets larger, okay, then this whole item on the left, the whole error gets smaller. All right, and so what's important for us is that we don't get anything bigger than 2. And what we're saying is that when this is equal to 2, and again, we had less than or equal to signs before, we can't have anything larger than 306.92. If it does get a little bit bigger, like, let me say it again. You can't have anything smaller, okay? If it did get smaller, then what happens is if this gets smaller, okay, then the entire error gets bigger. Okay, remember when your denominator gets smaller, it makes this fraction larger, okay, which means that it's going to actually grow bigger than 2. Okay, so this 306.92 is pretty much exactly 2. So, and the only way that I can keep it under 2 is if I pick values that are collectively under is if you pick something a little bit bigger than that. Okay, if you pick something too small, like pick something underneath it, like just plain 306, then this becomes smaller, which means this thing gets bigger, and now you're going to get a value bigger than 2 because 306.92 is exactly 2. Okay. All righty. That is all I have for you. Look at all the questions I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember, the first bunch usually ask for conditions, okay? So they're not all 3-step processes, okay? So keep that in mind. Last bunch are multiple choice. And if you have any questions, you let me know. I hope you have a great day, and we'll talk to you again soon.